Hey guys, it's Miss Willis. Today we're looking at mechanisms of ventilation for the respiratory system. So, ventilation simply means the air is going to move into the lungs and out of the lungs. So, obviously, that can happen through your nose or through your mouth. Get all the way down the trachea, split at the bronch tubes, when it continues to the bronchioles, all the way to the alveolar sacs at the edges of the tissuey part of the lungs that are going to be what expands for us, and back out. So within here, we're looking at the thoracic cavity. Our lung will be within here and within here. So we have our right pleural cavity. Pleural is referring to the lungs versus our left pleural cavity. The lungs are actually going to press right up against this cavity, and that's that suction that kind of connects the two of them together is part of what continually makes the lungs open and expand, is because it's going to be vacuum sealed to this, and then as air comes in and air moves out, pressure is going to change, causing that to continually happen. So when you look at the structures of the pleural cavity, on the outside part, we have the parietal pleura. The inside portion here is the visceral pleura. This is the part that actually bumps up against the organ itself, or is continuous with the organ itself. And then the pleural cavity is in between those two tissues. This is going to be fluid filled, and it's going to be just like the other cavities we've talked about. That lining is going to prevent friction from building up because there'll be fluid between it, so that when you rub your hands like this, it eventually gets hot. We don't want our lungs to get hot and have friction every time we breathe. So there's fluid in between that. If you put water between your hands and go like this, you don't end up with that heat. And so that's where the benefit of this setup comes from. So looking in here, we can see that we have that parietal pleura up against the rib cage, that visceral pleura up against the lungs. And you can see where that actually like folds in and everything, and goes wraps all the way around them. So for inhalation, everyone breathe in. And you can breathe normally afterward. But what happens? The external internal muscles, external intercostal muscles pull the ribs upward and outward. So when you look, so say that this is like where your sternum meets and these are the ribs hanging from it. When you breathe in, it expands and it opens. Your diaphragm contracts and it pushes down. And so that lifting up on the sides and that pulling down on the bottom actually causes the lungs to expand, because remember, they're attached to all of the pieces around them. And so if it's lifting up, the lungs are going to lift up. And if the bottom part is lifting down, it's going to stretch it open. And so now the lungs are open and air can come in. So the volume of the thoracic cavity increases. Pressure decreases. So when a bunch of volume has filled a container, pressure is lower within there compared to somewhere else. Remember that pressure actually is going to move similarly to how diffusion works. It's going to move from an area of high pressure to low pressure. So before you inhaled, the pressure within your lungs, obviously they don't collapse all the way shut, but that idea is that pressure is really low here compared to the outside atmosphere. It's actually negative compared to the outside atmosphere. And because of that, air is going to naturally flow in there and fill up your lungs. This is part of why you're able to breathe without thinking about it, and also breathe while you're sleeping, simply because of those pressure differences. So the lungs are going to fill as air rushes into the lungs. So as we look at this, this would be like in between breaths. When you breathe in, that diaphragm pushes down, your ribs open up. So that's what I was talking about with this, like that swinging action. Show it, like this is me trying to be dramatic with my ribs here, but obviously it doesn't move that much, but you can get the visual. Okay. So then if you inhale, Let me breathe out real quick. When you inhale, you can breathe in a little more. And then there's that much extra room, and you have muscles along your arms and your neck that actually help bring that excess amount of air into your body. Um, and so this is actually part of why they tell you, because that extra small little bit of air you don't need on a normal basis. People who are trained to sing are always told to make sure you breathe from your diaphragm and you're not constantly breathing from your shoulders, going and then breathing, because it tires you out a lot more. That excess amount of movement isn't usually needed. You don't Most of the time you don't need maximum inhalation unless you're like doing a competition for who can breathe underwater longest. For expiration, right? We're talking about breathing out. Um, our muscles and the elasticity of the lungs actually make it so that everything relaxes and moves back to its original shape. So the rib cage drops back down. The diaphragm shoots back up, and so then the volume within the thoracic cavity decreases. When this happens, the pressure within the pleural cavity actually has increased, and that's why the lungs expel the air. So compared to the outside environment, when air came into the lungs, then pressure built up. And so that's why after they've filled up, then they're going to decrease the amount that's in there. And again, that's going to happen naturally simply because of the pressure changes between the inside of our lungs versus the external environment, atmospheric pressure. So then when we exhale, our ribs go back down to normal position. Our diaphragm retracts back into its normal position. And then you can actually also maximum exhale. So everyone just exhale normal. Sorry, let me inhale normal first. And I exhale. And then I can push more out. Right? You can get more air out. That would be maximum exhalation. So with lung capacity, it's not just a matter of how much can they hold simply because they have the space for it. When you're first born, there's fluid within your lungs, right? The amniotic fluid that's been moving around. And so all those alveolar sacs are completely shut. And it's kind of like with a balloon. The very first breath you take into it, like this little kid's doing here, to actually get it to inflate takes a lot more difficulty than every other time that you blow up that same balloon. So they actually think that the first breath that an infant takes when they're born is 20 times more difficult than any breath that you take the rest of your life, simply because they haven't opened yet. The lungs haven't opened yet, and so it's really difficult to get it that very first time. So with that, we don't ever want, once our lungs open, once they inflate, we don't ever want them to fully collapse again. And so there's within those alveolar sacs, we produce a kind of a mucousy liquid called surfactant. And that's going to help that if those get really close together. I don't know, take two, if I had microscope slides, I'd show this to you. If you take two microscope slides and you put water between them, it is very hard to pull them apart from each other. It's very easy to slide them, like what we were talking about with the pleural cavity and that being able to move without friction. But to actually be able to pull them apart becomes really difficult. And so surfactant is more oily than water. And if the alveolar sacs were to get really close together, then that would still allow them. There's enough break in water properties that they'll still open back up. And so we produce that all of the time. So phospholipid, kind of a fatty type of oily substance, fatty, oily. but it reduces how strong that pull is if they close all the way. We don't want them to actually close all the way, so that also provides a padding to prevent them from actually squeezing all the way shut to each other. So then we can measure breathing intensities. We actually would have done this lab with peak flow meters where you basically go and it shows you the amount of volume and how hard you're able to breathe. And then being able to see that in a graph. So these wavy lines here, this is what your normal breathe in, breathe out. So just like as you've, I know it's always hard to like talk about this because when we talk about breathing, we change our breathing. But how it's happening normally when you're not thinking about it, just the I'm breathing through my mouth. But that in and out, that is called tidal volume, and that's what you find right here. Then there is all of this extra space. So remember we said we can breathe in. Just breathe in normal. Don't even like do like a big inhale. And then you can breathe in so much more. And all of that extra is your inspiratory reserve volume. So we have all this extra space to inhale more. And then same for exhaling. When you exhale normally, and you can exhale more. And even after that, so we have our expiratory reserve volume, that extra space for exhaling. Even after that, there's still some space. Remember, we don't want our lungs to collapse shut all the way. And so there's still residual volume after that. From the as much as you can breathe in to as much as you can breathe out. So if I go all of that I just did is my vital capacity, what I'm able to actually control of my breathing. But again, there's still that residual volume. Our lungs don't completely collapse even with as much as we exhale. And all of that, as much as we can possibly inhale, as much as we can possibly exhale, plus that extra bit, that is our total lung capacity. And so you're going to need to be able to view this chart and identify different parts of it as we move forward. And that's all for today. So I'll see you next time.